In your packet of learning materials for this unit on soil-water relations, you'll find this handout or reprint of an article entitled How Water Moves in the Soil by Dr. Gardner. Even though work was done many years ago and published, it's still very pertinent today. Inside of this handout, you'll find a number of illustrations or pictures, an example of which we see here, which is depicting how water moves under different types of situations. One of these has to do with textural stratification or layers of different textural soil within the soil profile. So as I refer to different types of water movement in the soil and different conditions that affect water movement, you'll want to have this handout on this article close by so that you can refer to it and follow along specific segments as we're talking about stratification, mulching, and other types of factors which affect the movement, intake and movement of water in the soil profile. This first graphic is illustrating the effect of textural stratification in the soil profile. I'm going to define textural stratification as any time we reach a layer of soil that is substantially different in textural class from the soil that lies just above it. In this particular example, we are looking at a soil profile where we have a coarser layer, such as a layer of coarse sand, underlying a more uniform or finer loamy textured soil above. Water in this case is being added from a flask into a notch or V that has been shaped into the surface of this soil. That is so that we can actually get a reservoir here to hold some water, which will allow a greater pushing effect or more water movement at a more rapid rate into this soil profile. It's representing water being applied such as in a furrow at one point of application. This is time lapse, and at 40 minutes from the time we initially start applying the water is moving in a semicircular fashion. We call this area right at the edge of where the water is moving into the soil the wetting front. So water moves, of course, laterally from this area of surface applied water as well as downward in the soil profile. So the shape of the wetting front would be rounded such as indicated here. Now when this wetting front reaches this layer of coarser textured soil, if we look at our time lapse, this is approximately 110 minutes, it reaches this layer of coarser textured soil, we would expect, because of the coarser texture and the greater hydraulic conductivity of a coarse soil than a loamy or finer textured soil, one would expect that water would move very rapidly down through this coarse layer. But actually, the opposite happens here. When we reach this layer of coarser textured soil, water does not move readily into that layer, and we get a buildup of moisture or water above that in this loamy soil to a much higher level than would normally be possible. If we go down here to approximately 400 minutes, then we're looking at eventually, as we build up a lot of moisture in this upper portion of the profile, we will eventually develop enough pressure or overburden here from the extra water that is not able to be held by this soil to where it will finally push itself through and begin to wet this coarser textured layer beneath that. Once this happens, then we will get more of a free drainage of water down into this region of the profile, and this soil above would come back to the level of water that it would normally be able to hold had we not had this layer of stratified soil down here below it. Well, what can explain why, as this water reaches this coarser textured layer, that it does not move into that layer? There are two things that help explain this. One is the fact that these coarse soil particles do not have as strong of an absorptive or pulling force for the water as do the finer sized soil particles above. In other words, the matrix potential of these larger particles is actually less than would be the matrix potential of smaller particles because of a greater surface area. The other thing that we need to realize that will affect this, these larger particles down here in the soil have a lot of trapped air in these large pore spaces. That air serves as a resistance to water, for water to move in there, so we have to develop a pressure overburden which has to overcome the resistance of the trapped air in this coarse layer of soil beneath that. So what actually happens here is that due to the trapping of air and the lower matrix potential of the coarse soil particles, we get a buildup of water above a coarse layer of soil buried beneath a more uniform or finer textured layer above. What would happen if this were a loam soil and this soil down here were a higher clay content soil, meaning a finer textured class? It would be very similar to what we have right here. In other words, if this were a fine layer of soil buried beneath a medium or a loam textured soil on top, we would also see a slower rate of water movement into this layer below. But that slower rate of water movement into this layer would basically be due to the lower hydraulic conductivity of that fine layer beneath. It would not be due to trapped air, it would not be due to a lower matrix potential. It would have to do with the fact that that fine textured layer just doesn't have the ability to transmit the water fast enough to keep up with the rate of transmittal of this loamy or textured soil above. So in summary, if we have textural stratification in the soil profile, whether that be a coarse layer or a finer textured layer buried beneath this more uniform loamy soil above, we will see a buildup of moisture above that layer of textural stratification. If it were a coarse layer, that could be an advantage to us in that we could actually see a higher water holding capacity, say in an irrigated situation, in the top part of this soil profile. If it's in a dryland situation and this is a finer textured layer down here, then obviously that would be non-desirable, because that finer textured layer, such as a plow pan or a hard pan, where we have less pore space to transmit that water through, or smaller pore spaces, actually is going to cause a reduced intake rate of water if it occurs close enough to the surface, which oftentimes plow pans are going to, if they're there, are going to occur in that top foot of the soil profile. This is reducing water intake at a time of year when we want to get as much water into and stored in the profile as possible. And therefore that stratification is generally non-desirable, especially if it's a finer textured layer beneath a more uniform loam soil above.